Hello students, today we are going to see a new lesson called Magnetism and Magnetic Effects of Electric Current. This is going to be the session 1 and today we are going to see the important topics: Introduction to Magnetism, Earth's magnetic field and magnetic elements, and some basic properties of magnets. Next one is the basic properties of magnets, which is very important. There are a lot of properties behind this magnetism. Let's see one by one. First of all, magnetic dipole moment. Here in this picture, you can see Qm be the pole strength of magnetic pole. Here the south pole and the north pole have Qm here, and L be the distance between the geometrical center of bar magnet O and the one end of the pole. So this is the one L and another L. Altogether we have 2L distance between the two poles, south pole and north pole. The magnetic dipole moment is defined as the product of its pole strength and magnetic length. It is a vector quantity and it is denoted by P vector m, and P vector m is equal to Qm into d. That means d is the vector drawn from south pole to north pole and its magnitude is modulus of d vector, which is considered as 2L because we have one L here and another L here. So the magnitude of magnetic dipole moment is Pm is equal to 2qml, like we have 2qa in electrostatics. Here the SI unit of magnetic moment is am square. Now we are going to see magnetic field. See, definition of a magnetic field, which is very important. Let me explain that. Now we are going to define the magnitude and direction of the magnetic field, which is entirely by reference to its effect upon the electric current. Without reference of magnets or lodestones, we cannot explain this magnetic field. We have already noted that if an electric current flows in a wire in an externally imposed magnetic field, it experiences a force at right angles to the wire, which we call that as an electric shock. Okay, this is to explain you about the flow of electric charges and the magnetism in between that charges. I want you to imagine that there is a magnetic field in your room originating perhaps from some source outside the room. This need not entail a great deal of imagination, for there already is such a magnetic field, namely which is Earth magnetic field. Probably you know more about the gravitational force. I will tell you that the field within that room is uniform, but I shall tell you anything about either its magnitude or its direction, because magnetic field have both attraction and repulsion. We know the opposite poles attract and the same poles repel each other. Now the magnetic field is the region or space around every magnet within its influence can felt by keeping another magnet in that region. The only one difference between the magnetic field and the electric field is the magnetic field attracts the object towards itself and it influences the magnetic energy or magnetic field towards that material. But the electric field never attracts the opposite or conductor, but it transforms its charges from this material to that conductor which is kept inside the electric field. The magnetic field B vector at a point is defined as the force experienced by the bar magnet of unit pole strength. B vector is equal to 1 by qm into F vector. It's Newton ampere minus 1 meter minus 1 is the unit for this magnetic field. Now let's see what are the types of magnets. Magnets are classified into natural magnets and artificial magnets. For example, iron, cobalt, nickel are natural magnets. Strengths of natural magnets are very weak and the shapes of the natural magnets are irregular. Artificial magnets are made by us in order to have desired shape and strength. If the magnet is in the form of rectangular shape or cylindrical shape, then it is known as bar magnet. Let me explain something about this bar magnet. A bar magnet has some properties that are quite similar to those of an electric dipole, which I show you in the earlier slide. The region of space around the magnet within which it exerts is magic influence and which is called as the magnetic field, and its geometry is rather similar to that of the electric field around an electric dipole, although its nature seems a little different in that it interacts with iron fillings and small bits of iron rather than the scraps of paper or pitch balls. Now let's see the properties of magnet. First one, a freely suspended bar magnet will always point along the north-south direction. Second point, a magnet attracts another magnet or magnetic substances towards itself, that I told you earlier. The attractive force is maximum near the end of the bar magnet. When a bar magnet is dipped into iron filling, they cling to the ends of the magnet. See, I have shown a bar magnet near a compass. When a magnet is broken into pieces, each piece behaves like a magnet with poles at its end. See, if you cut this magnet into pieces, this south and north have both the charges qm and qm. See, each piece have a south and north. Okay, both have the lengths also. Clear? So there is no difference in magnetic strength. Fourth point, two poles of magnet have pole strength equal to one another. It has been directed by the some materials. The length of the bar magnet is called geometrical length, and the length between two magnetic poles in a bar magnet is called the magnetic length. Magnetic length is always slightly smaller than the geometrical length because it have to show the poles. We measure the length only from the pole, not the from the end of the bar magnets. The ratio of magnetic length and the geometrical length is 5 by 6. You can see here the like poles repel and the opposite poles attract each other. So, using the ratio of magnetic length and geometrical length, we can have the magnetic length divided by geometrical length is equal to 5 by 6, which is 0.833. Now pole strength. Pole strength is a scalar quantity with dimension m naught, lt naught and ampere. Its SI unit is nt minus 1, that means Newton per Tesla, or am, ampere meter. Like positive and negative charges in electrostatics, north pole of magnet experiences a force in the direction of magnetic field, while south pole of the magnet experiences a force opposite to the magnetic field. Pole strength depends upon the nature of the material of the magnet, area of cross section and the state of the magnetization. Fourth point, if a magnet is cut into two equal halves along the length, then the pole strength is reduced to half. If a magnet is cut into two equal halves which are perpendicular to the length, then the pole strength remains same. So you have to be careful while you're spacing the bar magnets into two equal halves. The sixth point, if a magnet is cut into two pieces, we will not get separate north or separate poles. Instead, we get two magnets. In other words, isolated monopole does not exist in nature. I already show all this in the picture. Now let's see the magnetic field lines. Magnetic field lines are continuous closed curves. The direction of magnetic field lines is from north pole to south pole outside the magnet and south pole to north pole inside the magnet. Second point, the direction of magnetic field at any point on the curve is known by drawing a tangent to the magnetic lines of force at that point. And in the figure, the tangent drawn at PQR gives the direction of the magnetic field B vector at that point. The magnetic field lines never intersect each other. Otherwise, the magnetic compass needle would point towards two directions, which is not possible. The fourth point, the degrees of closeness of field lines determines the relative strength of the magnetic field. The magnetic field is strong where magnetic field lines crowd and weak whether the magnetic field lines thin out. Fourth, and the D, magnetic flux. Already you know more about the electric flux. Like that, this magnetic flux also resembles the same nature. The number of magnetic field lines crossing per unit area is called magnetic flux. The number of electric field lines crossing per unit area is called electric flux, and the number of magnetic field lines crossing per unit area is called magnetic flux. Pi b is the symbol. Mathematically, the magnetic flux through a surface area A in a uniform magnetic field is defined as pi b is equal to b vector dot a vector, which is equal to ba cos theta is equal to ba. Here theta is the angle between b vector and a vector. You can see the picture. Using that you can have a angle here between the area of cross section. Now let's see what are the special cases here. First one, when b vector is normal to the surface, that is it is theta is equal to 0 degree. You know 0 degree means cos 0 is equal to 1. Then the magnetic field or magnetic flux is pi b is equal to ba, and which is maximum. When b vector is parallel to the surface, then it is 90 degree, theta is equal to 90 degree. The magnetic flux pi b is equal to 0. That means suppose the magnetic field is not uniform over the surface, then the equation shows, and it can be written as pi b is equal to integral b vector dot d a vector. Magnetic flux is a scalar quantity because it does not have any direction. Then the SI unit of magnetic flux is Weber, which is denoted by the symbol Wb. Dimensional formula for magnetic flux is ml2 t minus 2 and a minus 1. The CGS unit of magnetic flux is Maxwell. So 1 Weber is equal to 10 to the power 8 Maxwell. The magnetic flux density. See, it's defined as the number of magnetic field lines crossing unit area kept normal to the direction of lines of force, and its unit is Weber meter minus 2 or Tesla. And the last point, uniform magnetic field and non-uniform magnetic field. What do you mean by this uniform magnetic field? Let's see. Magnetic field is said to be uniform if it has same magnitude and same direction at all the points in a given region, like this. Example, locally Earth's magnetic field is uniform. Non-uniform magnetic field. Magnetic field is said to be non-uniform if the magnitude or direction or both varies at all its points. Example, magnetic field of a bar magnet. Here you can see there is a variation between their distances. Okay, the directions all are different in non-uniform magnetic field. Now, thank you students. Study the lesson well, because it's totally a different topic. Some of you are confused with this electrostatics and magnetism. If you are well versed with your book, you can get the right answers.